All right. So in last class we covered mechanical system, in which covered translation system. Am I audible?
Yes,
Yes.
sir.
So we covered translation system, and we covered rotational system, where we talk about spring, dashpot, and mass, inertial mass, and like that we talked about torsional spring, rotary damper, and inertial mass. So today we'll go into a little bit detail how to build a mechanical system using building blocks. So building up a mechanical system using our building blocks, which is spring, damper, or dashpot. Third one is, so let's consider a simple system having spring and a dashpot or a damper connected to a mass element M. Okay, is we are applying force F. Okay. So we have to develop a mathematical model for this system. So we have these basic elements here. So all three basic elements are available. If you see the system model, you have F input, X as output, and you have spring, dashpot, mass, or block. Okay. So if you draw a free body diagram here, so spring and this dashpot will exert resistance. So force due to spring, force due to damper. So the net force exerted on mass M, which is MA, is equal to F minus Fs minus Fd. Okay. So MAF, and your Fs is Kx and Fd is Cv. Okay. So Kx C dx by dt, and Ma can be reduced to dx square by dt square. So your F is equal to M dx square dt square plus Kx plus F. Sorry. Plus C dx by dt plus Kx. Okay. So you got a mathematical model in terms of differential equation, where F is a function of x, where x is displacement and F is your applied force. So this is the mathematical equation, your mathematical model that can be developed for different system. So a mathematical model developed for a different system used to predict the behavior. So let's say our first example is, uh, let's say we have to develop a model for a machine bed mounted the ground, uh, in order to predict the effect of ground disturbance or vibration. So if you talk about your machine bed, let's say consider your lathe machine. So your lathe machine bed is made up of a cast iron. Why cast iron? Because cast iron exhibit very excellent damping properties. Okay, and cast iron itself is having graphite flakes in it, so which act as a lubricant also. So generally we use cast iron for machine bed, and especially for its good damping properties. Okay, so basically we have to develop a model for this machine bed. Okay, in order to predict the vibration. Okay, so first of all, there will be a mass element due to bed, that is mass of the bed. Okay, the stiffness of the cast iron material can be analogous to your spring system, and the damping property can be referred as a damper or a dashpot and spring, which is connected to a ground, and a input force will be there, input force, which is supplied to the ground during machining operation. We have output displacement. Okay, so for this system, you can clearly develop a model which is same as that of previous one. Likewise, a system model can be developed for a tire suspension system, vehicle suspension system. So we have a suspension system where we want to predict the behavior of the vehicle in different terrain, because in different terrain the suspension system will behave in different manner. Okay, so if you consider your suspension system, you have tire here, then a suspension system. Okay, and then above the suspension system you have your uh, vehicle body. So basically what you have here is mass of your car. Okay, then suspension system, spring and its dampers. Okay, then also you have mass of suspension. Okay, then for tire you have basically stiffness. Okay, so this represents your tire, this particular element represents your suspension system, this is mass of car, and this is your output. Okay, so this spring and dashpot and mass suspension, this spring and dashpot and mass element arrangement represent a suspension system through which you can predict the its behavior in different terrain. And in order to further complex the structure, you can also add seat and driver. Okay, so above that you can more complicate the system. So basically, uh, while developing any model, the thumb rule is that your model should be a real time, your model should be a replica of real time system, and it should not be complex. Okay, but it can be used to predict the behavior of a real time system very closely. Okay, so this is how you can represent the mechanical system with the help of string and dashpot element, and different mechanical system can be represented. And this, and through this mechanical system you can deduce the mathematical model which can help you to predict the behavior. Where here in case we are focusing on the behavior of suspension system in different terrain condition. Okay, so how to approach or how to develop a system. So there are certain thumb rule or procedures which one should follow. So first is to isolate the various components. First of all, you have to isolate various components and draw its FBD, that is free body diagram. Then identify the forces and write the modeling equation. What are the different forces involved? Let's say if you consider tire, you have F force here and only spring force here. So you can identify two forces here. Likewise, third is combine all equations of the various systems to obtain a differential equation. So first you have isolated and drawn a free body diagram. Then you identify the equation and you develop a modeling equation based on that. Identify the forces and develop the modeling. And then you combine all the equation, finally representing in a form of a combined differential equation, which represent the model of your system. So let's understand this with the help of a simple example. This is string K1, K2, mass M1, M2. You are applying a compression force F. Okay. Initial position of string K1 is 3. Okay. So first of all, you have to isolate the bodies. So here you have two bodies. One is mass 2. So you isolate it and identify the forces. You have to draw the free body diagram. F compression force is here and a resistance, because a spring force will resist the compression. So Fs representing K2. Okay. So if you develop the equation, that is net force, that is M2A is equal to F minus FSA2. Okay. So considering FSK2 will be K delta X. Here delta X is X3 minus X2. So K X3 X2. Coming to A here, A will be D, sorry, d square by dt square X3. Okay. So by putting all this value, you will get the first differential equation of the body 1 or mass 2, which is F minus K2 3 minus X2. Okay. So you rearrange the equation, you will get all right. Similarly, you isolate the other system. So here the other system is your M1, M1. Okay. So force by spring 2, because you are applying a compressive force, so this M1 will also compress it. Okay, that is Fs1, and this spring now, this Fs2 spring, K2 spring will resist its expansion, because when mass M1 moves down, so it will try to extend the spring K2 and it will resist, so that force will be in opposite direction. Okay, so what you will be having here, that force M1A is equal to Fs2. Okay. So here you decide your convention first. Okay. So if you want to take all upward direction force as positive, so you consider them as positive. Okay. But here, if you see from this case, here we are considering the upward force in negative, like what downward is considered as positive. So you will have Fs1 minus Fs2. Okay. Now M1 dt upon x2 minus Fs1 is K1, x2 minus x1. 3 minus x2. So you can rearrange the equation and you will get the values. Okay. So now here you can see, here you can clearly see that, sorry, this should be clear. So this K2 can be replaced. Okay. This minus K2 can be replaced. Okay. So how you will replace it? M1 K1 X2 minus X1 plus minus F. Okay. From this equation, from this. Okay. Let's say equation 1. So from equation 1, you can get K2. Okay. K2 X3 minus X2. And you can replace it. Okay. So that will be M. So total minus sign you are replacing. So it will be, the expression will be M1 D2 square dx2 dt square K1 X2 minus X1 plus M2 D2 X3 upon dt square minus F. So you bring F here. So K1 X2 minus X1 plus 2. So with this, you can develop a system equation. So first, what you have done, you have isolated M2 and M1. You have drawn the free body diagram, identified the forces. Okay. You developed the differential equation for individual cases, that is M2 and M1. And finally, you have combined. Okay. So you have combined the differential equation obtained from M2 and M1. And finally, you will get the uh, uh, mathematical model where f is the function of x2 and x1. Okay. So likewise, you can develop a basic system model equation. Okay. Now coming to your another component of a mechatronic system, that is electrical system. And in our first class of this unit, we have discussed that electrical system has three basic building blocks: a resistor, an inductance, and a capacitance. So let's have a look of the basic equations for this system. So first we will have resistance. So a resistance can be designated by the symbol. Okay, having resistance R, you have a potential difference of V and current I. So the base equation is quite simple. V is equal to IR, that is from Ohm's law. Okay. Next is your inductor. So basically inductor can be represented by this, having an inductance L, a potential difference of V, current I. Okay. So the potential difference is proportional to rate of change of current, that is VI by dt. You can remove this proportionality sign. Reactance will come. Okay. So I will be equal to 1 by L V dt. Next is your third building block, that is your capacitance. So Q, you have charge Q and potential difference V. Okay. So basically your potential difference is directly proportional to, or you can represent potential difference is equal to Q by C, and Q is equal to I dt. Basically current is Q1 minus Q2 for I dt when presented. Okay. 1 by C. Okay. So this is your another equation. So these are the basic equations for your resistance, inductor, and capacitor. So in case of electrical system, this inductor and capacitors are used to store the energy, and in case of resistor, the resisting element generally dissipate energy in form of heat. Okay, so that will be P equal to I V square by R. Okay, so as it is a dissipating element, so it is analogous to your dashpot. Now inductor is storing the energy, okay, and it is given by E is equal to half Lc square. It is quite similar to half mv square, so it is a mass element, analogous to mass element. And next is your capacitor. Okay, next is your capacitor, and for capacitor the energy is also given as E half Ev square. Sorry, this is the mass element, that is spring element. Okay. Now we have to develop a electrical system model. Okay, so basically building a model for electrical system. So in order to develop a model for electrical system, as your mechanical system follows basic law of physics, that is Newton law, here you are following Kirchhoff law. Okay, so first law, that is L1, that is algebraic sum of current at junction is 0, and second law, that is in a closed circuit or a loop, the algebraic sum of potential difference, that is V, is equal to applied EMF. Okay, so let's develop a system using this laws. So first consider a resistance plus a capacitor system. So you have a potential difference applied across a resistor and a capacitor. The supplied potential is V, I current, resistance, and the potential difference across the capacitor is, let's say, VC. So algebraic sum of the current in a closed potential difference is equal to applied EMF. So applied EMF is V equal to VR plus VC, that is from Kirchhoff's second law. Okay, and this V is equal to IR, and this VC is equal to I dt. Okay, so VC is equal to 1 by C. So you can get I from here, that is C dV. Okay, so your V is equal to, this I is C by plus R. So this is the differential equation you got for a resistance and capacitance system. Let's consider all three elements here, that is a resistance, inductance, or capacitor, applied. This is DC. So V is equal to VI plus VR plus VC. Okay, IR plus LDI by dt plus VC. Okay, from I is equal to C dV by dt, and di by dt you can from here. Okay, now you keep the values of I and di by dt, so you will get RC by dt plus LC dt square plus E. So this is a second order differential equation that you got for a resistance, inductance, and a capacitor system. There may be a case where any of the one element is parallel to another. So let's have a look. So this is potential difference VC. This is junction A. This is I1, 2, I3. L, C, R, junction A, I1, I2. Okay. So I1 is equal to I2 plus I3, and I1 can be equal to V minus V upon R. That is this this is junction A. So the potential difference across this resistance will give you the so the potential difference will be V minus
Sir,
VA. Yes.
hello, sir. Screen is not visible, sir. You are not presenting screen.
Yeah. Now hello.
No, okay, sir.
Yeah. So I think in between it got disconnected. Then also your I2 will be 1 by L. Likewise, see here you have VA as these are in parallel, so potential difference will be okay. Now you can combine this equation V minus V upon R is equal to 1 by L plus E. So this VA can be replaced by VC. Okay. So your V will come as RC plus R by L. Okay. So this is how your electrical system model can be developed for parallel and series, and your electrical and mechanical system are analogous to each other. Okay, so for a mechanical system, you have a second order differential equation, that is C dx plus kx is equal to F, and here you have R C by dt C is equal to V. So here, if you see this both equation, so in mechanical system you have force as a driving element. Here you have voltage. Okay, then you have mass element, which is analogous to capacitance. Then you have a damping element or dashpot, which is analogous to inductance. So your mass element, inertia mass, is analogous to capacitance. Then you have a dashpot, which is analogous to your inductance. Then you have spring, which is analogous to your. Okay. So this is how you can develop the analogy between electrical system and a mechanical system. Okay. So this covers your electrical system also. Uh, in next class, we will start with fluid system building blocks. Okay. If you have any doubt, you can ask me.
Excuse me, sir.
Yes, Abhilash.
Sir, in terms of that analogy, you said spring is analogous to resistance, no, sir.
Yes.
But in spring case, it generally stores energy, but resistance it
Yeah, yeah. That's what
dissipates energy, no,
I
sir.
am cross checking. That's what. Let me. Yeah. Sorry. You are correct, Abhilash. Actually, uh, spring stores energy, and uh, so basically the storing element will be considered as a analogous way, which is inductance. Sorry. And dashpot dissipates energy. So here resistance is dissipating energy. So that spring should be inductance. Sorry. And a dashpot should be your resistance element. Is it fine? What's your name? Abhilash.
Yeah, fine, sir.
I think I that's what. Kalyan, I need to upload the previous presentation also.
Sir,
That previous presentation I need to upload.
yes, sir.
So let me quickly share the slide. So so this we have covered. Basically, it's a repetition only, so we can. Yeah, it's fine. So we have covered today's topic. So thermal and fluid system we will cover in next class. Okay, and I will upload the presentation in that drive here. So Kalyan, you remind me once. Okay, if by today if I am not able to, I will upload it tomorrow. Okay.
Yes, sir.
Anything else? Any other doubt if you want to ask? No doubt. So shall we end our class here?
Um, yes, sir.
So if on next class onward, if it will ask for the password is same only. I don't know why it is asking. I also checked in Google, but there is no provision to do that. Okay.
Okay, sir.
Okay. So thank you all. So in next class we will cover thermal and fluid system. Okay. So I will be ending this meeting. Thank you once again.